The 4026 is a 5-stage Johnson Decade counter designed to decode and drive a common cathode 7-segment display. The IC can be daisy-chained to drive multiple displays for larger counts. It can drive a small 7-segment display, but cannot provide enough output current to directly drive higher current displays. Consider using external drivers like transistors if any segment is going to pull more than 24 milliamps. The 4026 does not have internal storage and will reset after power cycle. A power reset circuit is recommended to be sure that the counter starts at 0 when the power is turned on. Let's go over the 16 pins on the 4026. Pin 1 is the clock input. The counter advances 1 count on each positive edge transition of the clock cycle. In most cases, only the least significant digit will utilize the primary clock signal. Pin 2 is the clock inhibit. Taking this pin low will allow counting. Pulling it high will inhibit the counter to advance. Pin 3 is the display enable in. Pulling this pin low will keep the display on. If you need the segment to turn off, pull it high. Note, if you turn off the displays, the counter will continue to count. Pin 4 is the display enable output. This allows cascade control of the display if you are using more than one 4026. Pin 5 is the carry out. This is the carry over output pin when using more than one 4026. It will allow the next most significant digit in line to advance after transitioning from 9 to 0. Pin 6, 7, 9, 10, 11, 12, and 13 are the decoded output pins that connect to the 7-segment display. Pin 14 is the ungated C-segment pin. This pin can be used when dividing your counts by 12 and 60. This comes in handy when counting from the 12th hour or the 60th second. Pin 15 is your reset pin. Keep this pin pulled to ground when not in use. Taking it high will reset your count. And finally, pin 8 is your ground, and pin 16 is your power. When hooking up your output pins, you can see each segment has a designated letter. These are A through G. When displaying the number 1, only segments B and C are lit. If we were displaying the number 7, segments A, B, and C are lit. Some 7-segment displays may have a dot or a colon within the package. The 4026 does not drive these. This will require an extra circuit to turn these on. Let's put a 4026 on a breadboard and see how it works in action. On this board, we have placed a button to activate the clock inhibit, a button to turn off the display, and a button for reset. The clock will be fed externally and represented as a blue LED on the right side. Sending a clock pulse will advance the counter and display the next number until it reaches 9, and then repeats, starting back at 0. If we take the clock inhibit high, the counter will not advance. If we send the reset high, your counter resets and will not continue until it returns to low. Right now, the display is on and showing 0 because the display enable pin is pulled high, indicated by the orange LED in the center. When we pull this pin low, the display turns off. While we keep the display off, let's advance the counter 2 times. When the display turns back on, it shows 2. This demonstrates the counter will continue to count even if the display is disabled. This may be used to conserve display power or provide a variable duty cycle for display brightness. Let's add a second digit, which will require an additional 4026. We'll need to tie both resets and display enable pins together. The carry out pin will become the new 4026's clock. But wait, there is a pin labeled display enable out, right? That is correct. You could run the display enable out pin to the display enable in pin to offer cascade control. The display enable out pin does follow the enable in, but note there's a slight delay. Let's put it into operation. When the 4026 goes from 9 to 0, it now carries over the remainder. We still can stop the counting by taking the clock inhibit high But this only affects the 4026 that's driving the least significant digit, because that first 4026 has stopped counting. It's reframed from carrying over any remainders. We also tied together both the reset and the display enable. Let's test those out too. Taking reset high will now reset both counters. And finally, moving the display enable low will disable both displays. If you want a third, a fourth, or even a fifth segment, just repeat the process. The 4026 operates similar to the 4017. They both count to 10. However, the 4026 is designed to decode its output to drive each of the 7 segments. There are other ICs designed to drive 7-segment displays. For instance, the 4033, which shares the same datasheet, replaces display enable with ripple blinking, and the ungated C segment with lamp test. Others include the 4511, which takes a binary coded decimal input and decodes it to a 7-segment display, and the 4543, another binary coded decimal to a 7-segment decoder designed primarily for liquid crystal displays. If you like these videos, be sure to like, share, and subscribe.